The next thing we want to look at is something called the polarization of light. So let's get started. Before I can talk about the polarization of light, I want to remind you something about vectors. And we talked about vectors are things that have both a direction and a magnitude. And so if I push, it's not enough to say I'm pushing with the force of 10 pounds. To really fully characterize the force, you would say something like I'm pushing to the right with the force of 10 pounds. Because that's different from pushing to the left with the force of 10 pounds, right? So force is something that's called a vector. Now, when we were talking about work, I want to remind you of this example because this is relevant to what we're about to talk about with light. So here's a lady, she's pushing on a lawnmower and she's pushing at a downward angle. And what we said is that part of that downward force is actually pushing the lawnmower into the ground. And so that would be this part of the force right here. And this is labeled with a V because that force is pointing in the vertical direction. And then there's part of the force is going into pushing the lawnmower forward. And of course, that is labeled with an H because that part of the motion is horizontal. So you have vertical force and horizontal force. And these two parts of the force, the part of the force pushing down and the part of the force pushing horizontally, those are the total force which is pushing at this downward angle. And I want to point this out because this is something that we talked about before. And remember when we talked about work, we said that work was the horizontal part of the force times the distance. And so that's why we did this. We said, okay, this force is pushing down at this angle, but only this horizontal part contributes to the work. Well, in this lecture, I don't actually care about work so much as the idea that a vector can have different perpendicular directions. And so I've got this downward force, and I can represent it as a part of a horizontal vector plus part of a vertical vector. And these two guys added together give you that total force. And so the idea that a vector can be represented as a sum of two other vectors that are perpendicular to each other, that is actually something that's generally true, and it applies to many things beyond work. And actually, one of the places where it has an application is in the electric field of an electromagnetic wave. Now, we've seen this picture before. This is an electromagnetic wave. And we talked about the electric part is in blue and the magnetic part is in this pink color. I want to just look at the electric part, the part that's in blue. And remember, the electric field is oscillating back and forth, and it's strongest here, it's zero there, it's weak, it's getting stronger, it's getting weaker again, it's back to zero. And so you can see this oscillating electric field as this wave is traveling forward. These arrows are all pointing in one line. So they're going positive in this direction and then negative in this direction and positive and then negative. And so they're basically corresponding to an electron that's vibrating back and forth in this sort of a fashion. Now, if I have a piece of iron, let's say I've got a piece of iron and I heat that piece of iron so hot that its atoms and molecules are vibrating quickly enough that that piece of iron is actually making light. And so if you heat the iron up so that it's glowing, it's actually generating its own light. That light, we know, is called by charges vibrating back and forth. Now, in that piece of iron, some of the charges are going to be vibrating back and forth this way. Some of them are going to be vibrating back and forth that way, some of them at different angles. And in fact, every possible angle is going to have some atoms vibrating at that possible angle, generating light with electric fields vibrating in those directions. And so what we see here on the right is showing this sort of plane. And so each plane would be an oscillating electric field traveling along that plane. And so this plane that's straight up and down, that would correspond to an electron that's shaking straight up and down. This plane that's at an angle here, that would correspond to an electron shaking back and forth in that direction. And so every possible direction. Now, if you drew every single possible direction, it would just be a blob here. So we've only shown a few of the possible planes, but there are planes in between these planes that are not drawn that would have electrons vibrating in those directions as well. Now, if you think of the light as coming towards you, and you guys are looking at a computer screen, so the light is literally coming from the screen, out of the screen towards your eyes, there are electric fields vibrating up and down, there are electric fields vibrating left and right, and some vibrating at different angles. Let's take this electric field that's vibrating at this angle. Remember, any vector, and this is a vector. How do we know it's a vector? It's got an amount, how big the amplitude of vibration is. If it was a brighter light, it would have a bigger amplitude of vibration. If it was a dimmer light, it would have a smaller amplitude of vibration. So it's got an amount, the electric field has an amount, and it's also vibrating in a specific direction. So when you have both an amount and a direction that are important, that tells you that it's probably a vector, and in this case, it is. What that means is I can take that vector and I can represent it as part of the vibration left to right and part of the vibration up and down, two perpendicular vibrations. So any angular vibrations I can represent as a sum of up and down added together to left and right vibrations. And so this figure C is generally how we represent these two. We don't take the time to draw out every possible direction. We just draw the two most important, the ones going vertically and the ones going horizontally. Now, if I have some vibrations going at an angle, that could be represented as some of that vibration is left and right, and some of that vibration is up and down, and we can separate those out. Now, what does this have to do with this word polarization here? The light like this, where you have electric fields vibrating in every possible direction, we would call that unpolarized light. It's light that's not polarized. Now imagine you had some material where all the electrons were all vibrating vertically. You would only have up and down electric fields. You would have no left to right electric fields. We would say that that light is polarized light. It's polarized vertically. And if I had a material where all the electrons were only vibrating left to right, I would have a horizontal polarization. But if I've got all the possible vibrations, then it's not polarized at all. Now, it's not actually pretty easy to get all the electrons vibrating in one way, but what you can do is you can take unpolarized light that has the vibrations in every possible directions and filter out one set or the other. That is, filter out all the horizontal vibrations or filter out all the vertical vibrations. And when you've done that, so you have light with electric field vectors that are vibrating in only one direction, we call that light polarized. And the process of polarizing light is called polarization. And so here we can kind of see the electric field coming from a vibrating charge. So if I've got a charge vibrating up and down, it's going to make an electric field in this vertical plane. If I have a charge vibrating left and right, it's going to make an electric field oscillating in this horizontal plane. So this guy in A would correspond to vertically polarized light, and this guy in B would correspond to horizontally polarized light. Now, how can we filter out one polarization versus another? Well, remember, when light passes through a material, it creates a resonance in that material and gets the light to vibrate. Well, some materials have these long chain molecules that preferentially only vibrate in one direction. And so what you have is you have this light bulb, for example, from this flashlight is sending out unpolarized light. It's light vibrating in every possible direction, which we can represent as just an up motion and a left-right, an up-down motion and a left-right motion. And this is a material that only allows the charges in the molecules to vibrate up and down. So the electric fields that are vibrating left and right, it won't make these guys vibrate left and right. And so the light that gets through is actually only the light that's vibrating up and down. And so what we've done is we've taken unpolarized light and we've filtered out all the horizontal vibrating electric fields and left only the vertical vibrating electric fields. And if I pass it through another polarizer oriented the same way, I get the same thing. And so I would end up with the light passing through these two polarizers, and it's started out unpolarized, now it's vertically polarized. Now, here is a different scenario, and you can see the lines are representing the directions that this guy will let light vibrate. And so here I've got vertical orientation, and here I've got a horizontal orientation. And so here I've got unpolarized light coming from the flashlight. I've represented it just as an up and down and a left and right. And so once it passes through this vertically oriented polarizer, only the up and down vibrations are allowed. Now, when it gets to the second polarizer, only left-right vibrations are allowed, but there are no left-right vibrations because they've all been filtered out by the first polarizer. So the light will be completely blocked. There's a picture down below kind of showing the same principle with waves on a rope and some fence slats. And so if the fence slats are both oriented vertically here, you can imagine shaking the rope and the wave would travel through unimpeded. But if you take this second fence and you turn it on its side, when these up and down vibrations of the rope get here, they get struck by these fence slats and they're not able to pass through. Now, one of the things that's interesting is that most glare from non-metallic surfaces is polarized. And so you can see this is a block of material that is not a metal, but is, maybe it's transparent. And so you have incident light, and you can see both up and down and left-right vectors. So this is unpolarized. It comes in and it reflects off the surface. And what happens is only the left-right light is passed after the reflection, and the up and down vibrations are the ones that gets transmitted into the material. And so you get the left-right ones are the ones that reflect, and the up and down ones are the ones that are transmitted. This is true also on the surface of water. If light is coming in at the right angle and it strikes a surface of water and it reflects, the reflection gets polarized. That's why very often sunglasses are made out of polarizing materials. Now, some sunglasses just have dyes in them that absorb the light, and they cut down on the light, they cut down on all the light. But some sunglasses are polarizing materials. And so if you have unpolarized light, the sunglasses are going to take out half of that light because they only allow one direction of vibration to pass through and not the other direction of vibration. Now, here is why polarized sunglasses are sometimes better than the kind that just have the dye in them, because most of the things that you have a glare from have horizontally polarized light. And so if you have vertically oriented polarizers in your sunglasses, that will block out those reflected lights. If you're a fisherman and you're out on a lake and there's a glare from the sun reflecting off the surface of the lake, it's not fun when that sun gets reflected into your eyes. But if you have polarizing sunglasses like this, they're going to take out the glare but not take out other light. And so they just filter out the part that is annoying and let you see the lake for what it is. Now in this figure we see a lady holding up two sheets of polarizing material. Each sheet is only going to allow the light to pass through vibrating with the electric fields vibrating in one direction. Now here the two sheets are oriented in the same way. And so the light, it passes through the first Polaroid and it is reduced in half, and it allows only light vibrating up and down to pass through. And the second polarizer is oriented in the same way, and so it allows only vertically oriented light to pass through, but that's what's coming out of the second polarizer, so it's able to pass through the second polarizer as well. And so you can see this lady's mouth because the light coming from her mouth is able to pass through both polarizers, or both Polaroids. Now, in the second case, the first polarizer has been rotated by 90 degrees. You can see the long end is now left to right, not up and down. And so you can see the light coming from her forehead and her eyes because they're only going through the one polarizer. Down here you can see her neck because the light coming from her neck is only going through that one polarizer. But in the middle, where the two polarizers are overlapped, they're at 90 degrees angles to one another, so none of the light is able to pass through, and it just looks black. And so that's why if you have two polarizing materials that are 90 degrees relative to one another, this one only allows side-to-side vibrations, this one only allows up and down vibrations, and so if the two are overlapped, you get no vibrations because they're all filtered out. Here, only the left and right are passing through. Here, only the up and down are passing through. But in the region where they overlap, nothing can pass through. Here you see the same lady again, and she's put a third polarizer in between the first two, and this one's oriented at a 45-degree angle. And now suddenly you can see her mouth again. It's dimmer, but you can see it. Why is that? Well, the first polarizer only lets left and right light go through, but when it goes through the second one at a 45-degree angle, that allows the light to pass through all three polarizers. Let me draw a picture to kind of help show how this works. Okay, what I've drawn here is a picture of the middle polarizer, which is kind of at a 45-degree angle. Now the first polarizer, when the light gets to this second one, the first polarizer has filtered out all the light except the ones that are vibrating left to right. Now, the polarizer in the middle only allows vibrations through that are oriented at this angle. Now, remember how we said that any vector can be represented as a sum of perpendicular vectors? I can take this guy here and this guy there, and these two green ones are the two vectors that would add together to give you the red ones. And so basically what happens is that the light coming through the second polarizer is now vibrating in a different direction than it was before. And so when it gets to the third polarizer, it's no longer at a 90-degree angle from it, and it can still pass through it. Of course, more of it gets cut out. That's why it's dimmer. But this enables you to sort of see how the light can pass through all three. Now, this last slide about the 45-degree angle thing, this is a little bit tricky. If you don't really understand it, don't worry, I'm not going to test you over this. But the other slide, the previous slide, you need to understand how the two polarizers work together, because that's actually really important. All right, so that's how polarization works, and we are done with this chapter, and we're going to move on to our next topic in the next videos.